Hello, differential equation students.
Today is topic 27.
Where we are going to use some technology to explore the different kinds of solutions we can get when we're solving planar, linear, homogeneous systems with constant coefficients. I have gone ahead and actually filled in this table. In your notes, you'll see the last two columns are blank. I've also taken the liberty of numbering the examples 1 through 6. And I simply used Wolfram Alpha to find the eigenvalues. It was really fast. And then the solution types I filled in ahead of time, but we're going to see why we use these names for the different kinds of solutions in a moment.
Take note that in your homework, case 1, we say that the origin is an unstable improper node. In case 2, we say that the origin is an asymptotically stable improper node. In case 3, we say that the origin is an unstable saddle point. In case 4, we say that the origin is an unstable spiral point. Case 5, we say that the origin is an asymptotically stable spiral point. And in case 6, we say the origin is a stable center. So look for that language in your homework assignment.
As we saw from the last units, the manner in which we solve these systems was really dependent on the types of numbers that were the eigenvalues. We had one process for when we had non-real eigenvalues, and then we had another process when we had a repeated real eigenvalue, and then a rather straightforward process when we had distinct real eigenvalues. And what we're going to explore is two of those three cases. We're going to be doing where the eigenvalues are real and distinct, and then where the eigenvalues are non-real. And that's going to generate, and then we have several subcases, 3 subcases for each of those 2 general cases. And in the first case of eigenvalues are real and distinct, we're going to explore what happens when both eigenvalues are positive, when both are negative, and then when they have opposite signs. And then when it comes to non-real, we're going to explore what happens when the real part is positive, when the real part's negative, and when the real part is missing. First of all, we're going to tackle number 3. Well, I want to do that one first, and then we'll do the rest in order after that. And I went ahead and actually solved number 3. I turned it into a system where I had the coefficient matrix was the matrix mentioned here in example 3. And I solved this by hand, although you could just use Wolfram Alpha to do this really fast. I found the eigenvalues, and for each eigenvalue I found an appropriate eigenvector, and then I constructed the general solution.
Okay, we're going to be using dfield, dplane, that website that we used earlier in the semester when we did direction fields. But now we're going to do it for phase plane portraits. So go to the internet, and in your search type in dfield and pplane. You should see something that says the Java versions. Go ahead and click on that. Your website should look something like this. And last time we used this dfield one, and now you're going to download the pplane instead. I did need to download and install Java to make sure this was workable on my laptop. You might have to do the same. Anyway, when you download it, you'll see a symbol that looks like this, and if you see the Java logo there, then you know that you've got the compatible software to open this. I go ahead and do that. All right, I'm going to say OK here. Let's delete those messages. Let's put my input up here and then make this a little bit larger. Okay, like we've talked about in other videos, you do have to write your planar system as an actual system of 2 different equations where you have an x prime and a y prime, and then input those separately up here. And so I'm going to go ahead and we're going to do example 3 first. And the matrix was 1, 2, 2, 1, and so the top equation should be 1 times x, so just x, and then plus 2 times y. And then the bottom equation was going to be 2 times x plus 1 times y. And let's do our window from just -4 to 4 and -4 to 4. And then click Graph Phase Plane. All right, now just like before, if you click on a point, that's going to be like, hey, there's my initial point. Let's see what happens to a solution if I start, say, right here. And the direction of the arrows would indicate the way this is drawn. So where I click would be, say, time 0, and then as time goes on, this solution will travel this path. And if time went negative, it'd go back that way. And then you can click all over the place and see what these kinds of solutions all look like. Notice if I click closer and closer to the origin, you get some interesting results. And if you kind of stay away from the origin, in fact, it sort of looks like all the solutions are sort of heading towards the origin, but then are sort of repelled by it as well and go off a different direction. In this situation, when you have a real positive and a real negative eigenvalue, we call this collection of graphs, we call them saddles. That's the word we'll use to describe this situation. Now, I did say that if you started with an initial value that was a multiple of one of the eigenvectors in your general solution, for example, the first eigenvector in our general solution was 1, -1. If you want to clear all this, just say graph phase plane again, and then if you go up here to solution and hit this and say keyboard input of initial value, you can actually type in what you want your initial point to be instead of trying to click for it. Let's put that down here. So let's make our initial value be a multiple of the first eigenvector. So the first eigenvector was 1, -1. So let's just actually put 1, -1 in there. And let's go ahead and specify a computation interval. Let's say time starts at 0 and just goes to like 10. And then say solve. Alright, now what happened here was you're seeing just a little line segment. That's because we started at the point 1, -1, and then the solution simply wrote a line segment right into the origin. If you start anywhere, if anywhere on the line that was the same direction as this vector 1, -1, for example 2, -2, and then say solve, you're just going to start a little bit further away but still ride the same line segment back to the origin. If you started a negative multiple of this, so let's do -2, +2, it's going to just start, oops, I think maybe we should clear, let's see, graph phase plane, here we go. So this one started at -2, +2, and just rode that line right towards the origin. Now let's start with an initial point that is on the line generated by the other eigenvector, which was 1, 1. So let's start at 1, 1 and see what happens. And let me clear that and say solve. Right, this time, this is giving me an alert, I guess, that we got some going up to t equals 10 made this point go rather far away. Let's just ignore that. Anyway, the point started at 1, 1, and then it went away from the origin along a line that's been determined by that direction of the vector 1, 1. In other words, y equals x. In this case, the two lines, y equals x and y equals -x, that sort of make a crisscross right through the origin, those are lines that sort of define the regions of the saddle, if you will. If your initial point starts on one of those lines, then it will stay on that line. And in one case, it'll go away from the origin, and in the other case, the solution will head towards the origin. And if your solution starts anywhere off of these lines, like 2, 1, and say solve, let's clear that one first, you actually get a point that this is not writing a line. It started at 2, 1, and it's approaching that line, if you will. It's heading off towards infinity. Let's start down here in the let's go out to 3 and then -2. Let's put a point down in the fourth quadrant. There's that solution over there. Okay, let's just get rid of this and just click away again. So pretty much if you start anywhere on a point that's not on one of those lines, the line y equals x or the line y equals -x, you're going to have a solution that as time moves forward and moves backwards, you get a solution that follows asymptotes, diagonal asymptotes. Okay, and that's a saddle. Let's do the next case. So let me clear this. And let's go in. The next case we're going to go back to is example 1, where it was 2x plus y, and then x plus 2y. This is the case where both eigenvalues were positive. And if you do different solutions, you see all solutions head away from the origin. They sort of, as time moves on from 0, the solutions go away from the origin, following some curve. If you start really, really close to the origin, it'll just still go away from it. The only way that you can actually stay at the origin is if you start with the origin itself. All right, if you plug in x and y are both 0, plug them into this differential equation system, you're going to get x prime and y prime are also both 0, meaning that the point's not going anywhere. But any other point that you start at, other than the origin, the solution will follow a curve away from the origin, out of the frame of this picture. In this phenomenon, we're going to call these, this scenario, this is a nodal source. So imagine like the origin is a node, and it's the source of the solutions, right? The solutions like emanate from there, if you will, and go off towards infinity, off in some direction. So this is going to be referred to as a nodal source. Both x and y, since the lambdas were both positive, e to the lambda t is going to blow up to infinity, and that happens for both components of the general solution. The x's and y's just all go to infinity. They just go somewhere, plus or minus infinity, depending on what the c1s were. Let's call the nodal source. All right, let's do example 2 where both eigenvalues are negative. So the only thing I have to change here is make a negative 2x and a negative 2y. Okay. In this case, the e to the lambda, both lambdas are negative, so the e to the lambda t's are e to a negative t, and as t goes to infinity, those exponentials shrink to 0. So both terms of the general solution will approach 0, suggesting that all solutions should be approaching the origin. And these arrows are kind of giving that indication. Click somewhere, and the solution just heads off towards the origin, and as time goes to infinity, it just gets closer and closer and closer to that. Pretty much, you could argue that it reaches there effectively at some point, but technically it never quite gets there. And all solutions do that. They just head towards the origin, and as time goes to infinity, it severely slows down, or it sort of reminds me of Einstein's theory of relativity. The faster you go, time slows down, and you get closer and closer to the origin. The point never quite gets there. It just super slows down and never gets there. But they all head towards the origin. This is called a nodal sink. Like all the points are like a sinkhole in the ground, right? Everything just gets sucked into it. It's like a black hole. All the solutions are just pulled right towards the origin. Called a nodal sink. Okay, now let's go over to where we had complex or non-real eigenvalues, and we're going to do example 4. Let's clear that. And the matrix here in example 4 is said to have 2 x's but a negative y for the first equation, and the second equation was 1x and 2y, so positive 2y. All right, in this part, the real part of the non-real solution, the a, was positive. So part of your general solution is going to involve, each component of your general solution is going to involve an e to the lambda t, where lambda is a positive number. Sorry, I shouldn't say lambda there. It's going to involve an e to the at. Right? Our lambdas are a plus or minus bi, and the real part is a, and the e to the at is going to be involved in both of your components of the general solution. And since a is positive, e to the at blows off to infinity. So both components head towards infinity as time does. And you can see all the arrows, heading off the screen. The other components, there's some sine and cosines involved in our general solution, and that actually causes a spiraling effect. Let's go ahead and graph some solutions here. So as you pick different initial starting points, all right, if this is my starting point, the solution heads off this way. With negative time, it would head back towards here. But as time moves on, all of our solutions head away from the origin. But they do it in a spiral fashion. So we're going to call this also a source, but we're going to call it a spiral source as opposed to the nodal source. Now let's do the case where we had both eigenvalues were non-real, but the real parts were negative. And our matrix here involved having a negative in front of that x and a negative down here in front of this 2y. Everything else keep the same. In this case, the e to the ATs, a is going to be negative, and the e to the ATs, therefore, is going to be an exponential that decays to 0 for both components of the general solution. Will both shrink towards 0 as time goes to infinity. So you expect solutions to, again, approach the origin like they did in the nodal sink, but they're going to do it in a spiraling fashion this time. So we're going to call this a spiral sink. And all solutions head towards the origin, and as time goes to infinity, they never quite get there. Sort of slow down, and time goes on forever, you never quite get there. But anyway, it's a spiral where all the solutions are sort of sucked into the origin like a black hole again. We call this a spiral sink. It sort of reminds me of water being flushed down a drain. Spiral sink. Okay, and then the last case was when the real part was 0. And so in that case, we actually had a matrix that had no x's, but a negative 2y. So we have x prime equals negative 2y. And the other equation was y prime equals 2x. All right, we call this center. In a case like this, because the a is 0, there is no exponential component to your general solution. You have e to the AT, and a is 0, so you just have a 1. The exponential parts are not present. So your general solution just is composed of cosines and sines, and that's it. And it turns out that all your solutions are going to be following elliptical paths centered at the origin. So if you do an initial value here, it's just going to do a circular path and go around the origin. We get a bunch of different ellipses around the origin. And you can explore different matrices that yield non-real eigenvalues, but with a 0 real part, so where a is 0. And you're going to get, sometimes you'll get circles around the origin, sometimes you'll get sort of more elongated or diagonal-looking ellipses going around the origin. But this classification, we're going to call these centers because they're all ellipses that are centered at the origin, traveling around the center. And this is what your solutions do when you have non-real eigenvalues with the real part of the eigenvalues is 0. The a is 0.
The trace of a square matrix is the sum of the diagonals on the main diagonal. The main diagonal is this diagonal, as opposed to saying that diagonal. But the main diagonal is top left down to bottom right. So we have a general 2 by 2 matrix here written down, A, B, C, D, and we're asked to find the trace and determinant. Capital T stands for the trace, and D is the determinant. So let's go ahead and write those down right now. So the trace of this would just be the sum of the entries on the main diagonal, A plus D, lower d. And the determinant, capital D, is right, we do this times the product of that diagonal minus the product of that diagonal. So it's going to be A times D, and then minus B times C. So here's the trace and determinant of this general 2 by 2 matrix. Then find the characteristic polynomial and express it in terms of trace and determinant. Okay, this will be interesting. Let's go ahead and set up the finding the characteristic polynomial, which we do by doing absolute value looking bars. Right, don't put the little tails on here because that means just regular matrix. This means determinant of the matrix that we're about to write. And we do this A minus lambda, where we subtract lambda from the main diagonal. So D minus lambda down here, and the other entries stay the same. And we do the determinant of this matrix instead, and we create the characteristic polynomial. So the determinant of this, we're going to multiply these entries and then subtract, multiply those entries. So we get A minus lambda times D minus lambda, and then minus BC. Let's go ahead and FOIL this out and see what happens. All right, so we have A times D minus a lambda, right, from that, and then minus d lambda, and then plus lambda squared, and then we have this minus bc. And let's regroup our terms and put this in traditional order. Lambda squared. Then the two lambdas here, I'm going to factor out a negative and the lambda, right, from these two terms, leaving an a plus d. And then the constants, we have plus, there's an AD constant in the front, and then the minus BC, right? These are the terms that don't involve lambda. That's what I meant by constants. Minus BC. All right, then you should notice something jump out at you. The characteristic polynomial is lambda squared minus, the a plus d is really just the trace. So we could say trace times lambda, and then plus, and then AD minus BC, that's just the determinant over there, so we have plus the determinant. So here's our characteristic polynomial in terms of trace and determinant, and it turns out this is always the case. So we could have been using this shortcut all along to find the characteristic polynomial of a 2 by 2 matrix. Just do lambda squared minus the trace of the matrix, so just the a plus d to get that number, and then plus the determinant of that matrix. All right, so I'm reading our instructions up here. Let's see, we've done the first one. We found the trace and determinant, and then we found the characteristic polynomial and expressed it in terms of t and d. That's done. Now let's do this part here. We're going to find the eigenvalues and express those in terms of t and d. So now we're going to essentially set this characteristic polynomial equal to 0 and solve, and just use the quadratic formula to find the eigenvalues. Let's do that work. Let's change the size of this and do some work over here. Excuse me. So we're going to solve this equation. 0 is equal to lambda squared minus the trace times lambda plus the determinant. And we'll use the quadratic formula. So we do the negative of this coefficient, so that's just going to be the trace, plus or minus. And then we square the trace, so it'd be t squared, minus 4 times a, which is the leading coefficient, right? 4 times 1 times d, so just minus 4d. This is inside the square root. This is called, by the way, this t squared minus 4d. The part that's inside the radical, when you do the quadratic formula, the word is discriminant, right? Not to be confused with determinant. The determinant of a matrix and the discriminant of the quadratic formula, they're different things. And then to finish the quadratic formula, this is all over twice the leading coefficient, so all over 2. Okay, so this is about as far as we can say what the two eigenvalues are going to be. Unless I know what t and d are, I can't really take this much further. So let's make this clear and say that this is our two eigenvalues are given by this expression. We can calculate and find them. Okay, so we've done that part. The next is find the product and sum of the eigenvalues and express those in terms of t and d. So let's do that down here. It says product and sum. Let's do the sum first. That'll be easier. So we're going to say, hey, what's lambda 1 plus lambda 2? And I'm just going to add these two expressions together and see what happens. So lambda 1 we'll say is the one that involves the plus, and lambda 2 will involve the minus. So the first one is, and I'm also going to split this 2 up under each part here. So our first eigenvalue was the trace divided by 2 plus the square root of the discriminant. The discriminant was t squared minus 4d. Let me make this a little bit easier to see by making that larger. t squared minus 4d, and that's all over its own too. So here's the first eigenvalue, and add that to the second one, which is going to be the same thing but minus. So let's just copy this. But minus. Okay, so here's the two eigenvalues added together using, the quadratic expressions for them. And notice that we're going to wind up getting t halves plus t halves, so we're just going to get t out of this. And the other parts are going to cancel. Right? This part here is positive, but this one here is negative, and they're identical, so they're just going to cancel each other when you add. So we just get t. That's fascinating. Turns out that when you add the eigenvalues, you always get the trace. You always get the same thing as when you just look at the matrix and add the diagonals. That's very fascinating. Now let's do the product. And let me make that a little bit smaller, put it right there. And let's do the product next. So we're going to do lambda 1 times lambda 2. So I'm just going to take these two expressions. Let's copy that, put it here. But we're going to multiply instead of add. Okay, so there's what this looks like. You can put them all back over their own too now if you like. We can do that. Let's go ahead and do that. Put each of these over just over a 2, over a 2, like that. So there's the two different lambdas being multiplied. I'm going to multiply the 2's and make a 1/4 and pull out the 1/4. And then from there, I'm just going to have to FOIL the two numerators. All right, so we do t times t, that's t squared. And then we do t times that negative radical, so we have minus t times this radical, which is t squared minus 4d. And then we do the insides from FOIL process. That gives me the same term here, but positive, so plus capital T plus the trace times the radical of t squared minus 4d. And then when I multiply the two radicals, and one's plus, one's minus, and the radicals will cancel, so we get minus, and then the radicals cancel. Don't forget these parentheses. And this is the result of FOILing those two expressions. All right, let's see. Let me move this over a little bit. Let's see where this takes us. So we have the 1/4 in front. These terms, right, this term and this term are the same but opposite signs, so they'll cancel each other. So we just get that t squared in front, and then we're going to distribute this negative across those parentheses. So minus t squared plus 4d. Now the t squares cancel, and we get just 4d, but then we do 1/4 of that, and in the end, we get the determinant. Wow, this is pretty fascinating. So this work is suggesting that when you add the eigenvalues, you get the trace of a matrix, but when you multiply the eigenvalues, you get the determinant of the matrix. Let's go ahead and skip a couple slides and just verify that that's the case with the same examples we had from that chart from our last unit from 9.3. Here are our 6 cases, and the eigenvalues, I've already entered them in here. I got them quickly by just doing Wolfram, but they're also easy to find. And let's just confirm that the trace and determinant can be found 2 ways. So first example, let's look at the matrix to answer these. The trace is the sum of these two numbers, so the trace will be 4. And the determinant is the product of those two numbers minus this product. All right, so we do 2 times 2 minus 1 times 1, so we get 4 minus 1, we get 3. Right. You can get the trace and determinant from the eigenvalues instead. Add the eigenvalues gives you the trace, and multiply the eigenvalues gives you the determinant. Let's verify all 6 cases that this happens. I'm going to do the trace. Let's do the trace by adding eigenvalues. So I get negative 4. Now let's do the trace by multiplying eigenvalues. You get 3. Let's get the trace and determinant the other way. Trace is add negative 2 and negative 2. Add them, right? So you get negative 4. Determinant is multiply that diagonal and then minus multiply that diagonal. and we get 4 minus 1, we get just 3. Trace in this case, -1, let's do it by adding the eigenvalues. -1 plus 3 is 2, and the determinant is multiply the eigenvalues, you should get -3. Let's do it using the matrix. Right, trace is 1 plus 1, that's 2. Determinant is 1 times 1 minus 2 times 2. So we have 1 minus 4, we get -3 for the determinant. In the case of complex eigenvalues, this is still true. If you add, let's add the two eigenvalues together, 2 plus I plus 2 minus I. The 2's will combine to 4 and the i's will cancel. You should get a trace of 4. Right? Add these together. You also get 4. Multiply the eigenvalues. And let's do that work down here real fast. Right, we have 2 plus I. I'm going to multiply that by 2 minus I. Multiply the eigenvalues. We get 4. -2i plus 2i will cancel, and we get minus I squared. Well, I squared is -1, so that becomes plus 1, and we get 5. Right? When I multiply the eigenvalues, I get 5. Well, let's do the determinant here. We do 2 times 2 is 4, and then minus a -1. 4 minus -1 gives us also 5. Right? Right now, you should just be like marveling. This is fascinating. Trace and determinant and how they relate to the sum and product of the eigenvalues. What are we on? Fifth case. Add the two eigenvalues. Well, the i's will cancel when you add these together. You should just get -4, right? And add the main diagonal. You also get -4. Oops, let's make that a 4 again. Multiply the eigenvalues, right? We get 4 there. The I parts will cancel, right? So we'll get plus 2i, minus 2i, those cancel, and then we have minus I squared again. That's going to be 5. And do the determinant of this matrix, right? -2 times -2 is +4, minus -1, that's going to give us 5 again as well. And finally, let's do the last one, right? Add the two eigenvalues together. 2i plus -2i just 0 out. So we get 0 is the trace by adding the eigenvalues, but 0 is also the trace by adding the diagonal. And multiply the two eigenvalues, right? 2i times -2i, that gives me -4i squared. I squared is -1, so this will just be 4. And let's do product, or the determinant this way. 0 times 0 is 0, minus -4. 0 minus -4 is also +4. Okay, so we're able to get the trace and determinant multiple ways, by looking at the matrix or by working with the eigenvalues. Now let's talk about the different solution types by creating what's called the trace-determinant plane. The kinds of eigenvalues you're going to get determined the nature of the solutions, right? Whether we had spiral sources or spiral sink or a center or a saddle or a nodal sink or a nodal source. And those, the types of eigenvalues, whether they were real or not real, were determined by the discriminant, right? The part that's inside this radical, this t squared minus 4d. If that's positive, then you're going to get two real distinct eigenvalues. So you're going to be looking at either a nodal source, a nodal sink, or a saddle. If t squared minus 4d is negative, you're going to get two non-real eigenvalues, suggesting that either we're going to have a spiral source, a spiral sink, or a center. If t squared minus 4d is 0, then you get a single real repeated eigenvalue. And you'll notice we didn't bother doing characterizations for that case, and we're going to leave that off here as well. Let's just worry about when t squared minus 4d is positive and when it's negative, and what kind of solution we expect to get. Well, since everything is dependent on the discriminant, t squared minus 4d, whether that's positive or negative, I'm actually going to make a graph of t against d. Right, we have t on the x-axis, on the horizontal axis, and d on the vertical axis. And I'm going to solve this discriminant for D and make a graph. Right, so if I take that and solve for D, set this equal to 0 and then solve for D, right, you get D is equal to 1/4 of T squared. And when you graph that, D against T, it just produces a flattened parabola with a vertex at the origin, so the shape that we see here. Now, the region above this parabola, right, this corresponds, let's use some color coordination here. So if we're going to go above the parabola, right, so all this area up above the parabola, like all of it, etc. This corresponds to when D is more than 1/4 of T squared. Right? When D, which is the vertical component, is higher than that parabola, will be above the parabola. Well, if you get all the terms on one side, multiply by 4, and then move the subtract the 4D to one side, so I'm trying to recreate this expression. What would this look like? We would have 4D is more than T squared, and then subtract the 4D, and we get that T squared minus 4D is less than 0. So in other words, when the discriminant is negative, this is the region above this parabola. If your trace and determinant, for example, what if you were at a point right here where your trace was -1 and your determinant was 4, right? This will be in this area. This will be above this parabola. That would suggest that when your trace and determinant place you into this region, then your discriminant is negative, meaning that your eigenvalues are complex, they're not real, meaning that we're talking about spiral sources, spiral sinks, or centers. Right? But we have definitely non-real eigenvalues up in this area when your trace and determinant put you above this parabola. So we would have non-real eigenvalues. If your trace and determinant are such that you're on the parabola, then we have the one real eigenvalue. That's been repeated, but let's not talk about that case so much. So let's move on to being below. And I'm now realizing that above maybe sounds better if it's green. I don't know why. I'm going to make that green. There we go. And let's do below red. Just red is negative, green is positive. I don't know. So if we want to be below this region, all right, so all this stuff below so everything below, etc. You get the idea. Below this region is going to correspond to when D is less than the parabola. So D is less than 1/4 of T squared. And I'm going to produce T squared minus 4D. I'm going to multiply by 4. And then subtract the 4D. I'm trying to create an expression that involves T squared minus 4D. And in this case, that's more than 0. So if your discriminant is positive, T squared minus 4D, the term inside the radical, right, is positive. That means we're going to have two real eigenvalues that are distinct. And so in this entire red region, if your trace and determinant are such that you wind up in that red region, then that means that we are going to have either a nodal source, a nodal sink, or a saddle. Okay. So here we have two real distinct eigenvalues when your trace and determinant place you in that region. All right, we can take this a little bit further. We can also predict the type of the solution by using the trace and determinant of the coefficient matrix to determine which region of the image below is represented. Okay, so the type of solution, let's first explore this in the green. So when we have non-real eigenvalues. In that case, when we had non-real eigenvalues, so we're down here looking at this bottom case, if A was positive, then we had, if you recall the solution type, I should really just copy these over from the last one. Let me back up to our last notes. Just grab this and copy these over. Right, these were the solution types. If we have non-real eigenvalues, right, so we're looking at this case, and we have a positive real part, then we have a spiral source. Well, the real part is going to be, right, it's the A that's in front of the plus or minus BI. And when you look back at our quadratic formula, you know, if the discriminant here is negative, you're going to have some i's involved, but the real part, the part in front of the plus minus, is going to be calculated by doing the trace divided by 2. So if the trace is positive, then trace divided by 2 will be positive. And in other words, A will be positive. If trace is negative, then A will be negative. Okay, so that's going to help me. So we're focusing now just on this, this upper region. Let's go different colors now. So if we're up in here, we know that we have non-real solutions. And also, if the trace is positive, remember trace is the horizontal axis, if it's positive, then we're going to be looking at our top case here of spiral sources. Well, that's true if you're in this area. So we're going to get spiral sources here because we have non-real evals. Let's write that a little bit better. Non-real eigenvalues. Evals is just short for eigenvalues. And we also have the trace is positive. And since A is equal to the trace divided by 2, right, using the quadratic formula, since the trace is positive, we know A is positive, meaning that we're going to be working with some spiral sources. That's when the solutions all spiraled away from the origin, right, towards infinities. But when when A was negative, right, and since A is really just the trace divided by 2, so when the trace is negative, A will be negative, and that's going to give us a spiral sink. So in this picture here, let's use a new color. Let's go with, guess it doesn't really matter. Just pick something Weber. Okay, got it. This one. So we're over here is when T is negative, when the trace is negative. And the discriminant is also negative. So over here, we still have our non-real eigenvalues. And this time the A, which is the trace divided by 2, will be negative because in this region T is negative. So therefore A will be negative. And here we have spiral sinks. Okay, and then let's look at this last case down here. If A is 0, then we're going to have centers. You know, centers were all the different ellipses that were centered at the origin. And in order for A to be 0, if we look back at our quadratic formula up here, for A to be 0, knowing that A is going to be found by doing this part, you need the trace to be 0. So that's going to happen in this image right along that vertical axis. So let's do red for this one, and we have to make the pen a little bit smaller. So if you're on this axis but up in this region, you still have non-real eigenvalues. So we're still in the non-real space for the eigenvalues. But this time the A will be 0 because T is 0 along that axis. And so we have the centers. The centers just meant the ellipses. All right, so we've everything that's above the parabola, we've parsed the different regions to get a little bit more fine-tuning of the different kinds of solutions we expect to see. Now let's look at the red blob here, when the discriminant is positive and we get two real distinct eigenvalues. All right, looking at our chart here, so now we're focusing on this case here. If both eigenvalues are positive, then we're going to have a nodal source. When they're both negative, a nodal sink, and when they're opposite signs, we're going to have a saddle. Now let's actually do this by doing the saddle first, because the determinant, if the eigenvalues have opposite signs, then I don't necessarily know what the trace is going to be, right? It depends on which number was larger in absolute value. The trace could be positive or negative in this case. But what I do definitely know is that the determinant will be negative, because the determinant is found by multiplying the eigenvalues. And if the eigenvalues have opposite signs, then the determinant is going to be negative. So if you have a negative determinant and a positive discriminant, then you're going to have saddles. And since D is the vertical axis, in order for the D to be negative, we have to be below the horizontal axis. So let's go with a color for our pretty much anything that's below the parabola and also below the axis, the horizontal axis. So we're talking about a pretty big region. In other words, quadrants 3 and 4. This whole region, space down here, corresponds to real distinct eigenvalues and a negative discriminant. So we have real, comma, distinct evals, and we have a negative discriminant, which suggests that lambda 1 times lambda 2 is also negative, which means they're opposite signs. So we have saddles. Okay, let's see if we can figure out where these cases are going to happen. All right, so in the cases where both eigenvalues are positive or negative, the determinant will be positive. So that's going to put us in the either first or second quadrants, but we still have to be below the parabola. And the trace will help us. If the eigenvalues are both positive, then the trace will also be positive. All right, so let's do that top case first. So we need a positive determinant and a positive trace, but we have to be below the parabola. So positive determinant and positive trace, but below the parabola. That puts us in the first quadrant below the parabola. So we're talking over here. Oops. Now you get the idea. So if we're over in this area, then we have, here we go, we have our real distinct eigenvalues. The determinant is now positive, suggesting that the lambdas have the same sign. And the trace is also positive. And these together tell us that the evals are positive. Because when you multiply them, you need to get a positive number, and when you add them, you need to get a positive number. So the evals are positive, which means that we have a nodal source. Right? When the eigenvalues are positive, it means the solutions go to infinity. So that gives us the imagery of a source, like emanating from the origin. And then by process of elimination, right, at this point here, I think we feel pretty comfortable knowing how to get this last one. Let's do the darker green. Right, this area over here. Over here, we're going to have, again, real and distinct eigenvalues. We know that the determinant will be positive, but the trace will be negative in this area, and that means both eigenvalues are negative. Oops. This implies that the evals must be negative, both, which means that we have a nodal sink. All right, so this ultimately is our regions split up that help us. And if the discriminant is 0, oh, we're not going to explore it when the discriminant is 0, but when the, I meant to say determinant there, determinant 0. So we're not going to explore what happens along this axis, because that would suggest that the determinant is 0. And we're not going to explore what happens along the actual parabola, which is when the discriminant is 0. In other words, when there's one real eigenvalue repeated. But we do explore what happens in all the surrounding regions, and also what happens along this particular part of the vertical axis, which is also technically true. We also know what happens, we know pretty much what happens along the entire d-axis, but we're not going to worry about what happens along the t-axis or along the parabola itself. If you like, you can explore those options, but for the purpose of our class, we're going to stop our discussion here. So then when you're doing a problem like one of these problems here, and you're faced with the matrix, it's very easy to figure out what the trace and determinant are without even finding the eigenvalues, right? You just have to use the matrix to figure out what the trace and determinant are. Then you effectively plot that point. You say, okay, well, trace is 4, determinant is 3. That would put me up in here. And then you would say, sorry, 4, 3 does not put me up in there. Right, trace is 4. Discriminant is 3. That puts me in the pink area. I plotted that wrong. Anyway, 4, 3 would be in the pink region. And then you'd say, okay, if I'm in the pink region, that means I'm going to have a nodal source.